Good morning, everyone. Today, inshallah, we will continue on our topic, which started in the previous lecture. As I told you, everything you will find on Moodle, and also all the recorded sessions, you can find them on the YouTube. I want you to remember about the previous lecture. We handled, number one, the definitions of the vector function, simple curve, and regular functions. Number two, parametrizing various shapes and the quadratics. We saw the various forms that we can use in order to parametrize some of the famous shapes, like a circle, like an ellipse, like a parabola, like a hyperbola. And also we did go through, I've represented an ellipsoid in parametrization. So this is really a very important part. You should go through it before this lecture. Number two, the basic parametric representation for famous conics and quadratics, as I told you. Then the tangent line at a specific point. We already tangled this point. We had a problem. We solved the problem, I believe, and we will also continue from this point. Now, I want you to go with me on this problem while he asked you about determining the tangent line to the ellipse x squared over 4 plus y squared equal 1 at the indicated point, which is root 2 and 1 over root 2. As we saw in the previous lecture, in order to get the equation of the tangent line, I will get, first of all, r vector, then I will, as you know, differentiate it in order to get the velocity vector. Then I will start substituting with this point to get a vector. So now I have a point and the vector. Now we can write the equation or the parametric equation of the tangent line for this curve. First of all, I will have to start with parametrizing this curve. So the steps will go as follows. Number one, bold the equation in parametric form. So start to look by looking to this equation. Try to discover which type of conics or how to parametrize this equation. Of course, x squared over 4, y squared over 1 equal 1, which is an equation of an ellipse, so I will use the standard, the parametric form as you will see. Number two, get our vector of this shape, as you will see, the components of x and y. If we are in 3D, as we will show also, we will get x, y, and z. Number three, get the derivative of the r vector, as I told you exactly. Sub by the point to get the direction vector and the equation direction vector, and then write the equation of the plane. So everything will start with the parametrization of this conic. So x squared over 4 plus y squared equal 1. As I told you, it's an ellipse equation. So simply, this is the main form of, or the general form of an ellipse, which is x minus h to the power of 2 divided by a squared plus y minus k to the power of 2 by b squared equal 1. Here the center is h and k, and the semi-axes are a for semi-major x and b for semi-minor x. The first step is to both the assumptions. X will equal to h plus a cosine theta, y will equal to k plus b sine theta, where theta is the angle starting from 0 and with a complete cycle to 2 pi. So mainly I will use these two components replacing the x and y. For this ellipse in particular, you will discover that h and k, both the coordinates of the center, are zeros. And for the semi-major x and semi-minor x, this is going to be 2 and 1. This is why if I want to write x component, it's going to be 0 for the component of the center. So this guy is going to be 0 plus an a, which is the square root for 4, which is going to be 2 cosine theta. For y, we don't have y minus k, so k is equal to 0. So once more, this is going to be 0 plus b, which is divided by 1. That means 1 sine theta. And so this is what we will have? X equal to 2 cosine theta, y equal to sine theta. Now I have x, I have a y, x 2 cosine theta, y sine theta. Now we can get r, which is r equal to 2 cosine theta in the I direction and sine theta in the j direction. Now I have the I unit vector, which is the direction in the x direction, in the x-axis, and j, which is the unit vector in the y-axis. So we are in the 2 dimension, as you know. So this is r. Getting r, we now can get the value of r dash, which is the derivative of r, which is simply going to be negative 2 sine theta and cosine theta. Now I have r and I have r dash. I will need to find theta, which corresponds to the point that we have. The point given root 2 and 1 over root 2, they are given in Cartesian coordinates. So now I will have to get the value of theta corresponding to this point. So remark that this point is given by root 2, this guy is root 2, and 1 over root 2. While the x component, you already said that x equal to 2 over cosine theta and y equal to a sine over theta. So all I have to do now, I have the cosine component or the x component and the y component, both of them are positive values, which means we are in the first quadrant. Very good. So now I will have to solve the equation 2 of a cosine theta equal to root 2. And this will imply that cosine theta will equal to root 2 over 2. Just making a simple simplification for this value, you will end up having cosine theta equal 1 over root 2. Same way like it will go with the y component, which is exactly gonna lead to theta or sine theta equal to 1 over root 2. I'm associating in a triangle where both the cosine and sine are 1 over root 2, which is 45. So either using your calculator in order to get the value of theta, or building the triangle for cosine, which is gonna be simply 1 and 1 and root 2. This is theta, and sine theta exactly the same. So all of this will lead to theta equal to pi over 4. Now I know the value of theta. Now I have the value of theta. So from all of this, as I told you, this is the point in the xy plan. So once you have the point in the xy plan, I will make root 2 equal to 2 cosine theta, and sine theta equal to 1 over root 2, which will lead to that theta equal pi over 4. Now I have the point which is given. I will need the vector corresponding to this point. So all I have to do now is to substitute with pi over 4 in the r dash vector, or in the vector shape. So it's going to be minus 2 times 1 over root 2, and this is going to be 1 over root 2. Now I can write the equation of the tangent line. The point plus lambda, which is a constant, belongs to r, times direction vector, or the slope of this vector, or whatever. So all I have to do is just to make, as I told you, this is the first point, which is root 2. This is the second coordinate, which is 1 over root 2. This is lambda, and these are the values from r dash. So that's the equation of the tangent line. If you like to gather it together to have the I component separate than the rest of the j component, we can do that. We can write that the tangent line will be a value of I plus certain value of j. If I want to do this, I will take 1 over root 2 minus, root 2. So it's going to be 2 over root 2, So it's going to be a root 2. This is for the x component in the point, plus or minus, whatever, lambda times negative root 2. So it's going to be negative root 2 and lambda. For the rest of components, this is going to be 1 over root 2, and this is going to be 1 over root 2 times lambda. So it's going to be 1 over root 2 plus lambda over root 2, and that's the equation of the tangent line if you want to gather both of them together or to separate the I component from the J component. Perfect. This is sufficient, but if you need to put it on that form, it's going to be okay also, because maybe you will have a multiple choice result for this problem, so you will have to try to organize your result to be one of the alternatives, or to discuss or think of the alternatives to be an equivalent form for this one. Okay, perfect. Now going to the second point, or the second bullet in our discussion today, which handle the trajectories, velocity, and acceleration vectors. The trajectories of particles moving in plane or space, that's a concept in the parametric representation, or in spherical coordinates, or in the cylindrical coordinates. We usually treat shapes or surfaces as projections of certain points, okay, on the space or on the plane. So if we are talking about something in 2D, we will be talking about something in the plane. So starting from the origin, there will be a projection for the points that once you gather them all together, you will have an ellipse, a parabola, hyperbola, based on the various conditions that's controlling the movement of this projection, which is R, or the equation connecting these projections all together. In the same way like in 3D, also from the origin, X, Y, and Z, the origin, and starting from R and theta or phi, depending on the coordinate system that you are using, you are just spreading some points and connecting them together. This is why it was said to you here that trajectories of particles moving either in the plane or in the plane or in the space. Described by the parametric curve, this is the parametric curve, f of t in the direction of I, g of t in the direction of j, and h of t in the direction of k, where t belongs to the interval of this domain. That wise differentiation, the first differentiation will get you the velocity vector. The second differentiation for r will get you the acceleration vector, which is the rate of change of the velocity vector. Simple, nothing to worry about. If you need to identify the velocity or the acceleration of this particle at certain time, all I have to do is just after getting the derivatives of these values, I will substitute by t node in either the velocity vector or the acceleration vector, as I told you. Sometimes we will need to integrate the formulas that we have in order to get, if we have a velocity, we need to integrate with speed. We can integrate in order to get distance or displacement or whatever. So we may need integration of a vector function. The integration of vector function is exactly the rules like derivative of a differentiation or a derivative of vector function. So all I have to do simply is to integrate the various parts of this function. So f r of t equal f of t in the direction of I, g of t in the direction of j, and h t in the direction of k, where t belongs to I. The definition of this r vector or vector function, and it is continuous on the interval a and b, and you have b is greater than a. So integrating r, it means you will integrate the components in the direction of the I, the j, and k. So now I will start integrating f of t with respect to the t and so on. This is the x component, y component, and of course the z components come completely nice. Then after you integrate, you do your different integration, all you have to do is to start substituting by the integration limits, and voila, you have your result. That's a quick example and a direct one on this relation. Here is R2, which is equal to t squared in the direction of I, et in the direction of j, minus 2 cosine t. It's really very simple, And as I told you, try, while you are studying such stuff, try to use your pen, try to make integration happen, start using a pen and the paper. This is very major. So all I have to do, integrating from, he want me to find the value from 0 to 1 for the vector function parametrized in R. So all I have to do is to get integrating for t squared dt, okay, dt in the direction of I, plus integrating from 0 to 1, the second component, which is in a form of an exponential function with respect to j, plus integrating from 0 to 1 to the third component, which is negative 2 cosine t with respect to dt. So all I have to do now is just integrating t squared. It's gonna be t cubed over 3, and then I will start substituting by 0 and 1. For the second one, which is et, integrating is going to be e to the power of t, as you know from the exponential functions. Then substituting from 0 to 1. The final one, which is negative 2 cosine t. So integrating cosine t, you will end up having sine of t. So for the last one, I will have plus negative 2 of a sine t, and all of this, I will use the substitution from 0 to 1. So simply, all I had to do is to start integrating, then I will do the substitution. So this is exactly what happened. This is t squared in the direction of I, et in the direction of j, negative 2 cosine t in the direction of k. Integrate each one separately, very smoothly. So it's going to be t cubed over 3 et negative 2 sine t. Then start substituting from 1 to 0. Of course, in substitution, we will substitute by the first number, then by the upper bound of your integration limit, then by the lower bound of your integration limit. So it's going to be 1 over 3 minus 0 for the first one in the direction of I, plus I will have e to the power of t. Once you start substituting, it's going to be e minus 1, and this goes for the direction of j, and then finally negative 2 of a sine t, and that's in the direction of k. So these are the direction I, j, k, and these are the values, negative 2 sine 1, I'm sorry, because sine 0 is going to be 0. And this will leave you with this result. So that's about the integration vector. Also, the properties, the general properties of definite integration will follow up with you, because you are doing just a definite integration. So if you are integrating and you have a constant, the constant can be taken outside integration limit. If you have R1 and R2, so all you have to do is to just get the derivative of the first one, plus or minus the derivative of the second one. As you know, derivative can be distributed on sum or difference of various functions. Parameters of vector functions, we really did go through this. So for R, if you have x component, y component, z component in t, all I have to do is to make the substitutions and you will find your final result. Now, for a length of a curve, if I want to identify a length of a curve or the arc length of a certain curve, all I have to do is to just apply this rule, which is the magnitude of the speed, the speed vector under integration, or integrating the speed value. So all you have to do is to get the speed value, and then I will integrate it till the boundaries of this curve in order to get your results. So we will start by identifying the problem, then we will go through this integration rule. So you will need to memorize that for an arc, in order to evaluate a regular curve arc length or length, all I have to do by the steps is first of all trying to get dr by dt, which means the derivative of this function. After you get its derivative, try to get the magnitude of the velocity. then start integrating with respect to t and then substitute. For an example, to make your life easier and the direct one, consider the vector function which is cosine ti plus sine tj, which runs from 0 up to 2 pi. If I ask you about this particular curve, you should know it. This is a unit circle. This is a unit circle parametrization or represented in parametric form. Be the length of R, determine the length of C. So all I have to do now is just to follow the steps that we said previously. I will start with getting the R. From R, I will start to get R dash. So first of all, I will start to differentiate R in order to get the velocity vector, and then I will get its magnitude. So I will start differentiating cosine t, which is gonna simply differentiating cosine t will lead to negative sine of t. Sine t differentiation is gonna be a cosine of t. So cosine t differentiation negative sine t is gonna be cosine t. This is R dash. And then I will try to get the magnitude of this vector. How to get the magnitude of this vector? Getting the first component to the power of 2 plus the second component to the power of 2. So it's going to be sine squared t plus cosine squared t under square root. Sine squared plus cosine squared, because you remember the trigonometric relations, is going to be 1. So a root for a 1 is going to be equal to 1. So now I've made it very clear that we will go first getting the value of R, which is the represent the curve that we are dealing with in parametric form, differentiating it, getting it the velocity vector. Then I will get the magnitude, then divide them on each other according to this term. So now all I have to do is to start integrating on the integration limits from 0 up to 2 pi for the curve, which is, be careful about this, which is R, okay, I'm sorry, R dash, which is, R dash negative sine t cosine t, the magnitude, which is gonna be a root of a 1, which is 1, with respect to dt. So all I had to do is to substitute by this guy, which is 1, in this integration limit. Now, if I did that, so it's going to be from 0, once you integrate, it's going to be, as I told you, t, starting from a 2 pi and 0, so making the substitution, you will end up having 2 pi, which actually the perimeter of this circle. As I told you, from 0 to 2 pi, this is 1. Once you integrate, it's going to be t. Replacing t by 2 pi, so this is actually make a complete sense. Now for the arc length of a curve is given by integrating the speed. This is in depth the process that we can use in order to find the arc length function. And that's an important topic to talk about, because we will need it down the road also to either to get a parametrization of the speed vector or in parametric vector representation. So the arc length of a curve is given by integral of the speed of this norm, which, and this is why once you have R, I will start to differentiating, getting the R dash, and get the norm or the magnitude. Here are the general conditions and formulas for arc lengths. This is in details how to go through this process. So for C belongs to I, for the curve that belongs to the interval of definition, the arc length function that satisfies S of C equal to 0, it's going to be exactly as we saw previously, the magnitude of the speed or the norm of the speed vector from C up to T. Once you make the integration first, and then substituting by T, you will have your function. So this is mainly what's going to happen. If we are talking about curves and you need to be in the right direction of movement or in the positive direction of movement, you should move on your curve considering your left hand inside your curve. So if I have a curve like this, okay, so I will try to move not from here, and this is going to be the negative direction. The positive direction will go like this. If I am moving on this perimeter, my left hand will be inside to the inside of this area or region. And we will need that in the application of the double integration down the road, moving around a region or something. Okay, very good. The conditions for arc length calculations for a smooth curve parameterized. We will get first RT, which is a value x as a function in t, y as a function in t, and z as a function in t. I will get its speed or the norm of the speed, which is going to be the magnitude of this vector, and then we will integrate from t naught to t, which is going to give us the function that we are dealing with. Where r dash is the derivative of the velocity, so this is the derivative first, then I will get the magnitude of this guy here, which is the square root of each, the square root of the square of each component, as you can see. So now once more, all I have to do is to get r, differentiating it, then getting the magnitude of this vector, differentiating it first, getting the magnitude of this vector, then doing the integration, we will have our function that represents this arc length. Arc length is as a new parameter. Now I can consider s of t as the arc length function. We can parameterize the curve in terms of s, as we will see through the coming example. Okay, which means the new parameter directly represents distance traveled along a curve. So now we can get this presentation happen when new parameter will satisfy that ds by dt equal to r dash. Okay, for an arc length, this was about the arc length curve, function. If I need to get the arc length in specific, as we saw previously, I will get the magnitude of the speed, then I will substitute. If I have the function, I will start substituting just by the boundaries, and that's it. That's a very nice example to apply all the data that we went through on this example. So I have now r, which is cosine t, sine t plus 2t in k, which is like a spring or something. It's like a unit circle, and you are trying to open it around the z vector, so it's a spiral shape. And let c be the graph of r of t, as I told you. Determine the arc length s that satisfies s at 0 equals 0. Okay, all I have to do now is to start following the exact steps that we did go through. Recognizing the r of t, which is going to be simply cosine t in I, sine t in j, and the 2t in k. Running from 0 up to 2 pi. The second step is to get r dash. So this is going to be negative sine t, that's going to be cosine t, and this is going to be 2. Now I have r dash, as you can see. So this is r, and that is r dash. The second step, I will try to get the magnitude of r dash, which is going to be simply squaring each component from these components. So it's going to be sine square, cosine square, and then 4, as you can see. Negative sine t to the power of 2, cosine t to the power of 2, and 2 to the power of 2. Now I have the magnitude of this r dash. The following step is try to simplify it as much as possible. As you can see, negative sine, it's going to be sine square, cosine square. The sum of them is going to be 1. 1 plus 4 is going to be 5. So we have just root 5 for this guy. So now the formula for the arc length curve here is going to be really very simple. All I have to do is to just integrating from 0 up to 2 pi for the magnitude of r dash, which is a root over 5 with respect to the t. So you will end up having root 5t, then start making your substitution. So for the function, for the arc length function, I'm not going to use the boundaries from 0 to 2 pi. I will use the boundaries from 0 up to t to get it as a function. So from 0 to t, you will have root 5t, and that's the arc length. If you take s for arc length as a function in t, we now find the relation connecting s as a function in t, and we can get the inverse, that t equal to s over root 5. So I can leave it in the arc length, or to get the r as a function represented in the arc length. So now the arc length function, as I told you, just integrating from 0 to t for the function which is root 5. So it simply is going to be from 0 to t root 5 du. So it's going to be root 5t. If you want to evaluate this arc length from 0 to pi, all I have to do is just taking t and replacing it by pi. I will have it root 5 pi. Here we go. That's going to be a root 5 pi, as I told you exactly. So having the function and the s of 0 equal to 0, s at t equal to 0 will simplify your life as much as possible. Because once you have the arc length as a function in t and you want to evaluate from 0 to this value, all I have to do is to make this substitution and you will end up having your function s of pi equal root 5 of pi. That's it. Okay, parametrizing associated with the arc length. This is exactly the point that we were talking about, is once you have s as a function in t, I can get t as a function in s and start parametrizing my problem once more as a function in the arc length. This is what has been stated here. This is x, y, and z, which are functions in f of t, g of t, h of t, and t belongs to a and b. If you get the arc length of this curve, you will have s such that running from a to b into alpha and beta. Then, using the arc length formula, I can resubstitute getting x, y, and z as a function in t of s, g as a t of s. So instead of dealing with parametrization with the parametric value, I can parameterize it with the arc length value. So for this problem, that's a direct problem on what we did go through. We're asking you let x, y, and z equal cosine t, sine t, and t. As I told you, it's also a unit circle, and we have the z variable is t running from 0 to 2 pi. It is a very nice function, and you have the contour or the curve, determine the representation associated with arc length. Now I'm not asking you about the arc length myself, but I need to have the parametrization as a function in the arc length. So I will move with all the steps. I will start with, first of all, identifying r. R is going to be cosine t, sine t, and t. So this is r, which is going to be cosine t in the direction of I, sine t in the direction of j, and the t in the direction of k. Getting the derivative of this vector, which is simply going to be negative of a sine t, then cosine t, then 1. After getting r dash, we can get the magnitude of this vector, which is simply, it's going to be the square root of the squares of each component. So it's going to be sine squared, cosine squared plus 1. Both of sine squared and cosine squared, these guys, these two values equal to 1. So you will have root 2, which is going to be the value of this arc length. Now, for this magnitude of this vector. In order to get your arc length as a function, I will integrate once more from 0 to t for the magnitude of the arc length, which is root 2 with respect to dt, and this will leave you with root 2 equal to t. This is s equal to root 2 of t, which means the arc length as a function in the variable t. I can get t, okay, once more as a function in s, so it's going to be s over root 2, just getting the t in one side. Using this value in the r vector and replacing the t with the s will leave me with cosine s over root 2 in the direction of I. So this is x, y, and z. I hope you can see. This is x, y, and z. The first component is cosine, replacing the t by s over root 2. The second one, which is going to be a plus of a sine s over root 2 in the direction of j, plus the final one, which is going to be just under a second, which is going to be t, which is s over root 2 in the direction of k. And this is the parametrization that he was asking about, parametrizing this curve but in the arc length formula, or the arc length variable. So the arc length for t from 0 to t is simply integrating root 2, as I told you. So it's going to be root 2 and t. Now I have the relationship between s and t in front of you eyes, which is s equal to root 2 of t. Now I can get t, which is going to be s over root 2, as I told you. So now I'm getting the inverse relationship, okay, which is t as a function in s over root 2. Now I will start substituting into the original parameter function. So x, y, and z is going to be cosine s over root 2 sine s over root 2 and s over root 2. That's the function that we are dealing with, or we are handling. So the arc length parametrization is going to be x, y, and z, s over root 2 and s over root 2. We have a problem here, just a minor one, that now you are moving from t 0 to 2 pi into a new variable, which is s. So I need to find the new limits. So once t changes from 0 up to 2 pi, I have the relation connecting them, which is s over root 2. Now, or using s, which is this relation, which states that s equal root 2 of t. So if t equal to 0, this is going to be the values of s, or the corresponding limits of this parameterization, but with respect to the s value. So putting the t equal to 0 here will let s starts from 0. And t tends to 2 pi, or the upper limit is 2 pi. Putting 2 pi here will leave it to be root 2 times 2 root 2 of a pi actually. So this is the result. If t starts from 0 up to 2 pi, once you deal with the s variable, it will start from 0 and it will end up at 2 root 2. This is why here we use this relationship, which ensures that s belongs to from 0 up to 2 root 2 and pi. And that's the final arc length. R of s is going to be cosine